Hello everyone, this is Venkitesh from IIT Bombay, and today I will be speaking on the probabilistic degree of an n-variate Boolean function. This is joint work with Srikanth Srinivasan from Aarhus University. Let's start with the basics. We are interested in probabilistic approximations of Boolean functions using polynomial representations. So for an n-input function f, by an exact representation we mean a polynomial that agrees with the function f at every input. In fact, since we are working over the hypercube 0, 1 to the n, we can always reduce the monomials in such a polynomial representation and make sure that it's a linear combination of square-free monomials. And this will be a unique representation as a combination of square-free monomials and will be the least degree such polynomial. So by degree of f, we mean the least degree of an exact polynomial for f. We are interested in polynomial representations for probabilistic approximations. So a probabilistic representation involves an error parameter epsilon. So fix epsilon greater than 0 and an epsilon error probabilistic polynomial is a random polynomial, by which I mean a probability distribution of polynomials Q, such that a randomly picked polynomial from this distribution agrees with the function with high probability, 1 minus epsilon, for every input. So the randomness here is not in the choice of the inputs, but in the choice of the polynomials. And we need agreement with high probability at every input. And the probabilistic degree for error epsilon of f, we denote it by p degree epsilon of f. This is the least degree of any epsilon error probabilistic polynomial for f. And the degree of a random polynomial in this sense is just the maximum degree among all the polynomials in the support of that distribution. Now there's an obvious relationship between the p degree and the degree for a function. An exact polynomial is always a probabilistic polynomial because we have agreement with probability 1 at every input. And therefore p degree epsilon is in fact at most the degree for every epsilon. So let's look at some simple examples before we go ahead with our results. Take the majority function on 3 inputs. So a majority function outputs 1 when the input has Hamming weight at least half the total number of inputs and 0 otherwise. And an exact polynomial is x1, x2 plus x2, x3 plus x1, x3 minus 2x1, x2, x3. So the degree of majority is in fact 3. However, the p degree for error 1 by 3 for majority is just 1. And we can simply take a single random bit from among x1, x2, x3 uniformly. And that will be a 1 by 3 error probabilistic polynomial. Another interesting example is the OR function, which outputs 0 when the input is the n-bit 0 vector and 1 otherwise. And the least degree polynomial representation for OR in the exact sense is 1 minus product 1 minus xi. And therefore the degree of OR is n. But the p degree of OR is significantly less. For error 1 by 3, it's in fact log n. And this was proved independently by Beagle, Reingold, and Spielman in 91 and Tarui in 93. So let's move on to the question that we are interested in. For an n-bit Boolean function f, a coordinate I from 1 to n is influential for f at input x. If f at x flipped at I is not equal to f at x, where by x flipped at I mean only the ith coordinate xi is flipped, changed to 1 minus xi, and the other inputs xj are kept as they are. And we say f is truly invariant if every coordinate from 1 to n is influential for some input. So the main question is, what is the smallest possible probabilistic degree of a truly invariant Boolean function? And we'll fix the error to be a constant 1 by 3. And we'll abbreviate p degree for error 1 by 3 by simply p degree for the rest of the talk. This is in fact a more general question. It can be phrased for any complexity measure mu. What is the least value of a measure mu for a truly invariant Boolean function? And it has been addressed before for other measures. For instance, the degree of the exact representation. Nissan and Szegedi showed that the minimum degree is in fact at least log n minus big O log n, which was tightened by Chiarelli, Hatami, and Sachs recently to log n minus big O1. Another important complexity measure called sensitivity, which is interesting to us in the context of our talk as well. So the sensitivity of f is defined to be the maximum number of coordinates that are influential for f at any input. And Simon showed that the sensitivity is in fact at least log n minus big O log n. And this is in fact tied up to the additive log n factor. and it's attained by a function called the addressing function, which is also important to us in the context of this talk. Other two complexity measures, approximate degree and quantum query complexity, Ambainis and Dewolf showed that the minimum value for these two complexity measures for any n-variate Boolean function is in fact theta log n by log n. Once again, the lower bound is attained by variants of the addressing function. And our interest in this talk, as I said, is when mu is equal to the p degree. Unfortunately, for p degree, we don't know much. In fact, we don't even know what is the p degree of the OR function. We don't even know the exact answer. We only have bounds. On the upper side, we know log n, as I just mentioned. And on the lower side, we have essentially square root log n, which was proven recently by Harsha and Srinivasan. So there is a log n to omega 1 gap in the understanding of p degree of OR. And let me simply denote m sub n to be the minimum p degree among all the truly invariant functions. So m sub n is what we need to determine. And our result says that determining mn can be reduced to determining the p degree of OR. So we don't improve the log n to the omega 1 gap in the understanding of p degree of OR. Nevertheless, we show that the problem of determining mn can be reduced to this problem of determining the p degree of OR. So let's go to a result in the formal setting. So these are the bounds on the p degree of OR, and we have a log n to omega 1 gap. So it makes sense to assume that the correct answer of p degree of OR will have the form log n to the constant. So we'll assume upper and lower bounds of the form log n to the c plus minus little o1 for a constant c. And then our result says the following: for a fixed c between half and 1, if the p degree of OR is at most log n to the c plus little o1, then mn is in fact at most log n to the c by c plus 1 plus little o1. Similarly, if p degree of OR is at least log n to the c minus little o1, then mn is at least log n to the c by c plus 1 minus little o1. So let me once again show this in a figure. So in this diagram, the green lines are the upper and lower bounds on p degree of OR that we know. The red line is the correct answer of p degree of OR, which we don't know, and we suppose that it's of the form log n to the c. And what we show here is that if you fix the position of the red line, then the position of the blue line, which is the minimum p degree of n-variate functions, can be tightly determined up to the position of the red line, up to the knowledge of the height of the red line, which will be log n to the c by c plus 1. And there are some interesting quick consequences. So this is a slightly more detailed diagram. Here, the shorter green lines are in fact the lower and upper bounds on p degree of OR, which is square root log n and log n. And consequently, we will get the shorter blue lines, which are lower bound of essentially log n to the 1/3 and upper bound of square root log n. So this is what we knew about p degree of OR, and our result gives these bounds on mn. In fact, even more, if the correct value of p degree of OR is this longer green line, then our tightness of the lower bound in fact gives a construction of truly invariant function f, for which the p degree is in fact something like this longer blue line, which is significantly lesser than the OR function. So we also show consequently that there are truly invariant functions whose p degree is significantly smaller than the p degree of OR. So let me now give you an outline of the proofs. Let me start with the lower bound, and therefore we assume that the p degree of OR is at least log n to the c minus little o1. And here we are interested in the sensitivity of the function. So there is a dichotomy in the behavior when the sensitivity is relatively large or small. So recall that the sensitivity of a Boolean function f is the maximum number of coordinates that are influential for that function across all inputs. And our lemma, first lemma, says that the p degree of such a function f is at least log s to the c minus little o1, where s is the sensitivity. And how do we prove this? We simply look at restrictions. What are restrictions? So here a function nu is a restriction, and this is a function of the set of coordinates x1 to xn, and a subset of these coordinates are kept free. They are kept as they are, which is the meaning of this symbol star, while the remaining variables are set to either 0 or 1. That's it. So f nu is obtained from f via the restriction nu, where each xi in f is either set to 0 or 1, or xi itself as defined by nu. And for our proof, we consider random restrictions. So we apply random restrictions multiple times to f. and in an independent fashion to get f1 to fl random functions. And I don't detail it here, but we will combine these random restrictions and obtain the odd function on S inputs, where S is the sensitivity. And we already have the lower bound on the odd function, and that gives us this lower bound of log S to the C minus little o1. So that's essentially the proof idea. However, this is not enough because this result gives us the bounds that we require only if S is large. By large, I mean log S to the C plus 1 should be roughly log n. When S is small, so we have this lower bound of log n to the 1 minus little o1, which is nearly tight on the sensitivity given by Simon. If we take this bound, then we will simply get mn to be at least log n to the C minus little o1, which is a much weaker bound than what we are looking for. So how do we strengthen this? So we have to treat the functions with smaller sensitivity separately with more care. So let me start with a typical example of a function which has small sensitivity but high p degree, and that's the addressing function. It is easily described using a decision tree. So this is a decision tree representation of the addressing function on 3 plus 8 inputs. I'll say why it's 3 plus 8. So in this decision tree, the left edges are all corresponding to the value 0 and right edges correspond to the value 1 taken by the parent node. The red circles are the addressing variables. The blue circles are the addressed variables. So what does this do? We first pass inputs to the addressing variables, to the red circles. And that will define a unique path to a unique addressed variable, to a unique blue circle. And then once the addressing variables are set to specific values, the function value is actually the value that is specified to the addressed variable, to that unique blue circle. That's it. So that is the idea of the addressing function. Once you pass the values to the addressing variables, the function value is simply determined by the uniquely addressed variable. So more generally, there will be a partition of the variables into r plus 2 to the r variables. So x1 to xr are the addressing variables. And once you pass these addresses, that will correspond to a point in the r-dimensional hypercube. And for all such points, we have the addressed variables z sub a. Right? And this is what we just said. When you pass the address a to the first r inputs, the output is just whatever is the value taken by the addressed variable z sub a. The degree of the addressing function as a polynomial is in fact r plus 1, which is theta log n. And the sensitivity is also r plus 1, which is again theta log n. From the previous lemma that we just saw, this will say that the p degree of addressing function is at least omega log n, because the sensitivity is log n. But in fact, the p degree is much larger. So how do we see that? It's quite easy to see that if you keep the addressing variables x1 to xr free and instead restrict the addressed variables z sub a to the function values f of a for every a, then the function f can be obtained from the addressing function by these substitutions as a function of the addressing variables x1 to xr. So any function with r inputs can be obtained from the addressing function using these restrictions. So in particular, we pass it to random restrictions. So through random restrictions, we'll get a random function. And our lemma says that the p degree of a random function on r inputs could be as large as omega r with high probability. And under restrictions, the p degree can only reduce because we are essentially going to a smaller function. Therefore, the p degree of the addressing function is at least omega r. But the degree itself is r plus 1. And therefore, the p degree is theta r, which is theta log n. So the whole crux of our proof is that this phenomenon of sensitivity being small but p degree being large for truly n-variate functions is essentially captured completely by the addressing function. What do I mean by that? So if you take any function with low sensitivity, then you can pass it through suitable projections and in fact find a copy of a function that looks quite like an addressing function inside. And that will be useful in determining a lower bound. So that's the title of this slide. Under projection, f looks like an addressing function. So what's a projection? Projection is simply a reassignment of the variables. So it's a function that starts with the set of variables x1 to xn and passes it to a fresh set of variables y1 to ym. And this is interesting in our context when the new set of variables is in fact significantly smaller than the initial set of variables. So we start with a truly n-variate function f and pass it through a projection. And we'll get what we call a pseudo-addressing function with parameters r and t, where r is polynomial in S and t is at least n by polynomial in S. And the pseudo-addressing function is what I mean by something that looks like an addressing function. So more precisely, we don't really characterize such a projection. We just pass through random projections and show that such a statement holds with high probability. So let me tell you what do I mean by a pseudo-addressing function in a more formal sense. So this is exactly what I mean when I said we will find a smaller copy of something that looks like an addressing function. So an R, T pseudo-addressing function is simply any function that is expressible via a decision tree having R addressing variables and T addressed variables, satisfying some conditions. And those conditions are very similar to what we just saw with the addressing function. So instead of detailing them, let me just show you an example. So let's take a decision tree for a function f. This is a truly n-variate function. The number of variables here is 10. And we'll show that there is a projection. So when you pass through a projection, what do you get? So first of all, some paths will disappear. So for instance, the rightmost path at the bottom from x4 to x10 to the leaves, they become redundant under this projection and therefore they disappear. That's okay. And now, after passing through the projection, this looks like a 4,5 pseudo-addressing function, where we have 4 addressing variables y1 to y4 and 5 addressed variables z1 to z5. And what's the property that we note here? So pick any node that contains an addressed variable. So let's pick the node w, which contains z4. There are 2 paths that originate from this node w, which terminate at leaves taking different values, 1 and 0 or 0 and 1, such that along these 2 paths, I have noted them as pi w1 and pi w0. Along these 2 paths, there are only addressing variables in the remainder of the paths. And the values taken by those addressing variables is consistent. They agree with each other, right? The assignment is consistent. Moreover, if you look at the path that starts from the root up to the node w, which is sigma w in this case, the green path. Once again, there are only the addressing variables in this path except the node w. And therefore, if you take the union of sigma w with pi w1 and pi w0, there is only one occurrence of an addressed variable w at the node w itself. Every other occurrence, every other node contains an addressing variable and their assignments are consistent. So once you fix the values of the addressing variables on this path, the function value only depends on the value assigned to the addressed variable at the node w and nothing else. And that's precisely the property we observed with the addressing function as well. So that's why we call this a pseudo-addressing function, because we have simply relaxed a little bit on the decision tree representation, but the behavior is quite similar to the addressing function. Okay. So under projection, f looks quite like an addressing function, but what do we gain from this? So we start with a decision tree tf, pass it through a projection rho, and we get a decision tree tf rho, where f rho is an r, t pseudo-addressing function, where r is at most polynomial in S and t is at least n by polynomial in S. And these functions are easier to analyze. So our lemma says that an r, t pseudo-addressing function will have p degree at least omega log t by log r. And therefore, since we have passed through projections, and once again, the p degree can only decrease since we are getting a smaller function, the p degree of f now is at least omega log n by polynomial S divided by log polynomial S. And this essentially completes our analysis, putting this bound as well as the earlier bound together and optimizing for the value of sensitivity, we get our required bound. So let me now conclude with a remark on the upper bound. The upper bound is much simpler. So this is what we have to prove. If the upper bound of p degree of r is log into the c plus little o1, then mn is at most log into the c by c plus 1 plus little o1. And as I already mentioned, the minimum approximate degree of truly invariant functions was studied by Ambayanis and Dewold, and they gave the tight bound of theta log n by log n. And they also gave constructions of variants of the addressing function for which this bound is tight. What we do is we simply adapt one of their constructions to our p degree setting, probabilistic degree setting, and obtain their upper bound. So I'll not elaborate on the construction, but instead just leave with this remark that we simply adapt their construction. So our tight example is also a variant of the addressing function. So that is as far as the details of the proofs go. I hope this outline was good enough for you to get a flavor of our results. And I encourage you to have a look at our paper for more details. Thank you.